Guys, I don't understand about the chapter 2.
Dude, I don't know how to do this either.
I think we need someone else to teach us.
Aizam, should we buy some donut after class?
Yeah, sure. That's a good idea.
Yeah, I'm feeling so hungry right now.
Yeah, me too. What are you guys doing?
Well, we're trying to study, and let's just say we don't understand quantifiers and
Rule of inference.
basically.
Let me look. Oh, this question. Lucky for you guys, me and Aizam already studied this chapter last night. So, we will help you solve this question.
Wow, that's a good idea, right? That's a very good idea. I'm not against it. Okay, how about I will teach you guys about the rules of inference, and Alex will teach you guys about the quantifier.
Okay, sounds like a good idea.
Okay, let's start with the rules of inference.
Firstly, let me explain about what is rule of inference. Rules of inference is one of the methods to determine the validity of the argument involving more than 3 propositions. There are 8 types of rule of inference that you should know, which is modus ponens, law of syllogism, modus tollens, rule of conjunction, rule of disjunctive syllogism, rule of conjunctive simplification, rule of disjunctive amplification, and rule of contradiction. Let's look at the example 1. We have P implies Q, Q implies negation R, S or R negation S or T, and N negation T, therefore negation P. We need to prove this argument is valid using the rules of inference. Firstly, we need to list down all the premises from 1 until 5, like I did. After that, number 6, we get P implies negation R from 1 and 2 using law of syllogism. Number 7, we will get negation S from 4 and 5 using disjunctive of syllogism. Number 8, we will get R from 3 and 7 using disjunctive of syllogism. And lastly, we will get negation P from 6 and 8 using modus tollens. So, this argument is valid. Now, let's look at example 2. We have P implies R, R implies S, negation S or T, negation T or U, and negation U, therefore negation P. We also need to prove this argument is valid using the rules of inference. So, firstly, the step we must do is, like I did before, we need to list down all the premises from 1 to 5. After that, number 6, we will get P implies S from 1 and 2 using law of syllogism. Number 7, we will get negation T from 4 and 5 using disjunctive of syllogism. After that, number 8, we will get negation S from 3 and 7 using also disjunctive of syllogism. And number 9, lastly, we will get negation P from 6 and 8 using modus tollens. So, this argument is also valid. For the last example, we have P implies R, negation P implies Q, Q implies S, therefore negation R implies S. So after we list down all the premises from 1 until 3, we will get number 4, which is we get negation P implies S from 2 and 3 using law of syllogism. After that, we will get number 5, negation R implies negation P from 1 using contrapositive. And lastly, we get number 6, negation R implies S from 4 and 5 using law of syllogism. So this argument is also valid.
So, what is quantifier? Quantifier are words that refer to quantities such as sum or all. It tells for how many elements a given predicate is true. Quantifier are used to express quantity without giving an exact number. There is 2 types of quantifier. One is universal quantifier. The second is existential quantifier. The word that used for universal quantifier is for all every, and for existential quantifier, the word that use at least, some, and there is exist. Let's move to the example 1, which is universal quantifier. Let Px be a statement for x plus 1 more than x. When we substitute 1 into the statement, we'll get 1 plus 1 is greater than 1. So that statement is true. When we substitute 2 into the statement, we'll get 2 plus 1 is 3. 3 more than 2. So that statement is also true. So we can say that for all positive integer s, Ps is true. Let's move on to the example 2. Still in universal quantifier. Let Px be a statement for s minus 2 less than s. So when we substitute x equals to 1 into the statement, we'll get 1 minus 2 is negative 1. Negative 1 is less than 1. So that statement is true. When we substitute 2 into the statement, we'll get 2 minus 2 is 0. 0 is less than 2. So that statement is also true. So we can say that for all integer x, Ps is true. Okay, let's move on to the last example, which is example 3. Existential quantifier. Okay, let Qs be a statement for s less than 2. So when we substitute 1 into the statement, we'll get 1 less than 2. So that statement is true. But when we substitute 2 into the statement, we'll get 2 less than 2, which is false. So we can say that there is exists positive integer s in Qs is true.
Okay, do you guys understand?
Oh yeah, definitely. Thank you very much.
Yeah, good. Actually, we are having a problem on solving chapter 3.
Oh, which part?
Which part is it, Aizam?
There is 3 parts, which is forward-backward method, mathematical induction, and specialization method.
Oh,
Yeah,
so that's
that
what
one.
you're having trouble with. Okay, okay.
Well, we can definitely help you guys. So I will teach you guys with forward-backward method. I will teach you about specialization method, and
That's right.
Spider will help you with mathematical induction.
Absolutely.
Now sit down. Okay, let me start. Assalamualaikum. So I will talk about forward-backward method. So forward-backward method is method to prove if A then B is true. So A is hypothesis and B is conclusion. A will do forward method and B will do backward method. So for example 1, if n is odd and m is even, then n m is even. So A will do n is odd and m is even. B and m is even. So from B we will get B1 and m equal to 2k, k element to integer. A1 n equal to 2a plus 1, m equal to 2b, which is a and b element to integer. So from A1 we will do A2 and m equal to 2a plus 1 multiply with 2b, then we express it, we will get 4ab plus 2b, then we factorize it to ab plus b, then let ab plus b equal to c, then A3 will get 2c, c element to integer, then we will get A3 equivalent to B1. Example 2. If n is even integer, then n squared is even integer. So we will do hypothesis and conclusion. A n is even integer, B n squared is even integer. Then B1 n squared equal to 2k, k element to integer. Then A1 n equal to 2a, a element to integer. So A2 we will get n squared equal to 2a square. So we express it, we will get 4a square, and we will factorize it to 2a square. So we will let b equal to 2a square, b element to integer. Then A3 we get 2b, b element to integer. Then we get A3 equivalent to B1. So next, example 3. Prove if the triangle RST with sides of length R and S and hypotenuse of length T satisfies T equal to square root of 2RS, then
triangle RST is isosceles. So for this question, we will draw it to make it simple. So A, RST is triangle with side of length RS and hypotenuse of length is T. Then B, RST is isosceles, which is R and S is equal. So B1, R equal to S. A1, we will do theorem Pythagoras. T square equal to S square plus R square. Then we can put T equal to square root 2RS to T square, which is square root 2RS square equal to S square plus R square. Then we can simplify 2RS equal to S square plus R square. Then S square plus R square minus 2RS equal to 0. Then A2, we factorize it, we will get R minus S equal to 0. Then A3, we will get R equal to S. Then A3 equivalent to B1. That is forward-backward method.
Now let's move on to the specialization method. Now I'm going to start off with the first example. So example number 1 says that if R is a subset of set S of a real number and U is an upper bound for set S, then U is an upper bound for set R. So the hypothesis here is that R is a subset to S and that U is an upper bound for set for set S. For the conclusion, then it's U is an upper bound for set R. Okay, to show that U is an upper bound for set R, we must first let X or all values of X be an element of set R. So from the hypothesis, we understand that R is a subset of S, so we immediately can tell that if we choose Y as an element of set R, therefore it is also an element of set S. Okay, from the hypothesis, U is an upper bound for set S, is what it says. Then for every element in B, which is an element in set S, B will be less than or equal to U. So since Y is an element to S, therefore it is logically assumed that Y is less than or equal to U. Hence, YU is an upper bound for set R. Now let's move on to the next example. Example number 2. Alright, example number 2 states that if R is a subset to S and S is a subset to T, then R is a subset to T. So the hypothesis here is the first sentence where it says R is a subset to S and S is a subset to T, and the conclusion would be R is a subset to T. So to show that R is a subset to T, it must first be shown that for all values of X is an element to R and X will be an element to T. So we then let or choose Y as an element of R. So based on the hypothesis where it says R is a subset to S, that would mean that Y is an element to S. And again, based on the hypothesis S subset to T, that would mean that Y is an element to T. Hence, YR is a subset to T. Let's move on to the final example. The final example states that if R is a subset of S on a set of angles and tangent equals to sine over cos on set S, then tangent equals to sine over cos on set R. That is the statement, of course. The hypothesis, or rather A, would be R subset S and tangent equals to sine over cos on set S. And the conclusion, or rather B, would be tangent equals to sine over cos on set R. Okay, in order to show that tangent equals to sine over cos on set R, it must first be shown that for all X is an element of R, giving us the tangent X equals to sine of X over cos X. Then we then let Y be an element of R, giving us tangent Y equals to sine Y over cos Y. Then based on the hypothesis, as you can see here, for every element B in set S, tangent B will be equals to sine B over cos B. And since Y is an element of S, based on the specialization here between A1 and A2, therefore tangent Y equals to sine Y over cos Y. Hence, tangent equals to sine over cos on set R. Alright, that's all from me.
Now, let's move on to the mathematical induction. Mathematical induction is the one method for proving that the statement Pn is true for every natural number n that is there infinitely in many cases. In this method, we have three steps. First step, we must show that P1 is true, and the second step, we must assume that Pn is true, and the last step, we must show that Pn plus 1 is true. So let's take a look for the first example. For all integer if n is more than or equal than 1, which is k is equal to n times n plus 1 is divided by 2, where k is 1 plus 2 plus 3 plus n. So we will use the three steps for this case. For the first step, we should show that P1 is true. So we need to substitute n is equal to 1 for the left hand side and the right hand side, and we will get the same answer, which is 1 equal to 1. For the second step, we must assume that Pn is true. And the last step, we must show that Pn plus 1 is true. So we need to add n plus 1 for the both equation for the left hand side and the right hand side. And the last equation, we will get that n plus 1 times n plus 2 is divided by 2. Let's look another example. For every integer if n is more than or equal to 1, 1 times 1 factorial plus n times n factorial is equal to n plus 1 factorial minus 1. So, we will use the same three steps like the example 1. And for the first step, we must show that P1 is true. So, for the left hand side and the right hand side will be the same, which is 1 equal to 1. For the second step, we must assume that Pn is true. And the last step, we must show that Pn plus 1 is true. So, the both equation left hand side and right hand side, we will get the same equation, which is n plus 2 factorial minus 1. Now, let's try another example to understand it. For every integer n is element to the positive integer, which is 3i minus 1 is equal to n times 3n plus 1 is divided by 2. So, we will use the three steps for this example. For the first step, we must show that P1 is true. So, substitute n is equal to 1, and the left hand side and the right hand side we will get the same, which is 2 is equal to 2. For the second step, we must assume that Pn is true. And the last step, we must show that Pn plus 1 is true. So, the left hand side and the right hand side equation must be the same in the last. And the last equation, we will get the 3n squared plus 7n plus 4 is divided by 2.
Conclusion to this video, me and my friends have fully understood and taught ourselves on one of the few subtopics of MAT222. Like Aizam and Haris have taught us the rules of inference and quantifiers from chapter 2, and we understand when to apply them, especially in logical situations. And me, Aidil and Iskandar have taught them the subtopics from chapter 3, where we learn 3 out of multiple methods in proving prepositions, like whereas Aidil has taught you forward and backward method, I have taught the specialization method, and Iskandar has covered mathematical induction. All in all, thank you very much for taking your time to watch this video, and we're sorry in advance for any and all mistakes that have occurred along the way. Thank you very much.
Do you got it?
Yeah, we got it. Thank you.
How about we treat you with some donut?
Alright, sounds like a good idea.